So now that you have seen the beauty of this cut matching game and how we generate different cuts and how we create edge, let's see how well the worst of O log 2n cuts SL and SL bar. How well this approximates the sparsest cut in G. And we use the property that the union edge of the O log 2n, I mean edge is the union of all matchings. The T is the last round, and we use the property that this union of O order of log 2 matchings can be embedded in G. So the congestion is at most order of congestion is at most the order of Cmax log 2n. And Cmax, you know, it's like a Turing machine. I mean, you have several numbers that are coming out, and you want to see which one is the maximum. For example, at round 1, you have C1. At round 2, you have C2. And round 3, T, you have CT. And among all of these rounds that you get your capacity, you can get the Cmax, the maximum of all of them. So this is the worst case, really, because the capacity, if you consider all of them are bad events, I'm using the terms of Loas, bad events, I mean, very bad, I mean, all of them the worst case. And so we are that much unlucky that we get all of them the worst case, then we can say the congestion is less than order of Cmax log 2n. So Cmax is the maximum of all CL. So the cut player's strategies is to ensure that H is an edge expander with expansion at least 1/2. So for any cut S and S bar, we can say that the number of edges of H crossing this cut, number of edges from S and N to S bar, is at least S/2. So bound on the congestion, let's say bound on congestion, this implies that the number of edges that cross this cut is order of S/Cmax log 2n. And this itself is the expansion is order of 1/Cmax log 2n. And this procedure greatly generates a cut of expansion at most 2/Cmax. So let's analyze the find bisection procedure. Find bisection. So in the T plus 1th ST round, there are several ST rounds, really. The cut player is given some. So the latest sparse graph that we have achieved is at time t, at round t, is this. So the cut player wants to find a bisection that any perfect matching across the bisection, when added to ht, so plus, when added to it, that improves its expansion. And t-step or the random walk is the tool that we want to use. So in step L, the particle stays put with probability 1/2 and traverses the incident match. So if it is matched, it traverses the particle is here, then it goes here with probability half, again half. So it stays here with probability half and traverses with probability half as well. So in step L, the probability of being at each endpoint is replaced by the average of those two probabilities. And the cut player. Now the cut player assigns to each vertex initial weight of 1/n, and the signs are chosen just a flip of a fair coin. And now the average of these weights according to natural random walks associated with M1, M2, MT. And then we define the bisection by selecting the n/2 vertices with smallest weights. So this goes here, and then we select n/2 vertices that have smallest weight. So as we think about h of t as a graph having several well-connected components, like this, for example. Several well-connected components, and they are somehow connected. So it's good connection. It has a good connectedness. And so each component, as you see, each component of all of this is H. Each component, which is highly connected, each component has a good expansion, but different components are very sparsely connected to each other. For example, one like this is enough. One is like this is enough. And now under averaging procedure, as I said, the weights rapidly achieve their average within each well-connected components. And these average weights for each components are typically non-zero because of the random initial weight assignment. So we select n/2 smallest weights, as I said. That should help separate some of the well-connected components from the rest. Let's say we are separated negative from positive. And the analysis is based on viewing this procedure as a random projection of a high-dimensional process. I mean, this is facilitated by choosing the initial weights according to a random unit vector rather than the discrete distribution. So we pick so the algorithm is just, we pick a random unit R in Rn, which is R is orthogonal to one vector. I mean, this is one vector, 1, 1, 1, 1, 1. And so we have n vertices, so this is n by 1. And then the second half, so U is just matching of several matchings until n1 of R. So what happens to this vector R comes out, and U, we get U, which is a vector itself, and then we just pick those half of them and n/2 of them, so half of this, in order to half of the largest, half of the smallest values, and that is your cut. So you have S n/2 of them, and your S complement is n/2 of them. So this is the cut. And this is what I wanted to say, but we call the procedure walk embedding. So the cut player does walk embedding. And I recall that this is our sparse graph, H, M1, MT, and T is the T step of the random walk, because at each round, the random walk creates the player. It creates just one of these matchings, and we have T different matchings. So it is a T-step random walk. And in step I, the particles stay put half over 2 and traverses half over 2. I just review this. And the Pij of T is the probability that the T-step random walk started at vertex J and ends in vertex I. So started at vertex J and ends in vertex I. So this is the probability. And the walk embeddings is like going from, so we're represented as a vector, but for example, we have a vertex I. Vertex I goes to this vector, which is Pi1, Pi2, Pin. For example, Pi2 is the probability that that random walk started at vertex 2, ends in vertex I. This is started at vertex N, ends in vertex I. So for any vertex, we have such a vector. And the Pi, you can represent it as Pi1, Pin, but transpose of this. And because the probability of being at node I is like Q times Pi, so because Q is initial, we don't know the initial distribution. And then this is the probability of being at node I. So finally, I can summarize that we compute the walk embedding, the process that I explained, and then we project onto vector R, which is orthogonal to the one vector. So because we project into a vector, it means you get a number, you get a scalar. So at round t plus 1, you get ui is pit dot product with your random vector. This is random vector, and this is pit. For example, in MaxCut, you have a vector that you have to solve. Here we have pit, vector of probabilities. And so the spread of the walk embedding, or let's say potential function psi of t, some people call spread, psi of t is a spread. This is the sum over pi minus 1 over n squared, and you can write it by definition as pij of t minus 1 over n squared. And so this means that this is a measure of the progress for a cut matching game. So it's a measure of expansion of HT. In other words, it's a measure of how evenly our H is distributed at time t. And I just say that we have a lemma in this article that say psi of t, if psi of t is less than 4 over n squared, then the expansion of ht is at least half. And the proof, so expansion is at least half. The proof is very simple, because if psi of t is less than 1 over 4n over 2, if you just look at that, you see that, okay, so Pij of t should be greater than 1 over 2n. And for any ij, Pij of t plus Pji of t is at least 1 over n, and then we can say the graph P of t has expansion greater than half. Very simple. And finally, I want to solve the max flow problem. I mean, in G, you have a source. As I said, this is a fake source. You connect it to all of the vertices of your graph, to all of them. And even in the sink side, you connect all of them to the vertices. And then your cut is like this. You cut from here. So we have B complement and B. So all of them has weight 1, 1. But the rest of them has C. The weight of the rest of them are just C. So, for example, all of them are C. And if this is something like this, this is incident to S. This edge is incident to S. And so we add source and sink until with, of course, unit capacity edges and capacity C for any edge. The flow of value n over 2, as I said, we fix the flow to n over 2 in order to always remember that black box. You want to see what C should I give in order to produce the fixed flow. And this is your solver, max flow solver. So the flow of value of n over 2 is used to find the fractional perfect matching between S and S bar. And this means that the max flow corresponding to capacity C flow problem can be decomposed into a perfect matching that can be embedded in G with congestion as at most C. And there is a important lemma in this article, lemma 3.7, that says if S and S bar be the min cut corresponding to capacity C half, in feasible flow problem, then the expansion is at most 2 over C. And moreover, if the max flow is of value n over 2 minus V, then each side of the cut has at least V vertices. And I can show you the proof in a graphical thing, so that, for example, you have S, you have S bar. Some of them, let's call it, so we have S, and this edge is incident to S. So if the number of such edges is n plus, and if this happens in the target as well, the number of these incident is n minus. So the number of edges going across like this is at most n over 2. This is the flow, minus n plus minus n minus over C over 2, because we have assumed from the lemma. So if the flow has the value less than n half, by the max flow mean cut theorem, the minimum cut, the separating source